In this video I want to cover two of the more common issues that we want to check when we're running OLS multiple regression, specifically issues of multicollinearity and checking for whether a couple of our cases are exercising undue influence on our regression results and therefore might be considered outliers. So what we're going to do is I'm using the state level data set and we'll regress a measure of social capital at the state level, social capital index, and we'll regress that against a measure of ethnic polarization and a measure of income inequality, Gini. And hit return. And we'll notice that combined, those two variables, ethnic polarization and income inequality, explain 61% of the variation in social capital across states. That's pretty good. Both of those variables are significant, EPI at the 0.01 level and Gini at the 0.01 level, and they both exercise a negative effect on social capital. So as ethnic polarization goes up, social capital goes down. As income inequality goes up, social capital goes down. If we wanted to do a better job of comparing the relative effect sizes of EPI and Gini, since they're on very different scales, we can just include the beta option. And see that, in fact, despite having very different unstandardized regression coefficients, that once we look at the betas, they actually have very similar effect sizes on social capital. Okay, so that's our regression model, and let's say that's the final regression model we want to look at. Some of the things we want to be concerned with is whether, in fact, our two independent variables are highly correlated with one another and therefore suffering from multicollinearity. Now, the fact that both of them are significant suggests that that may not be a problem. Usually what happens with multicollinearity is you'll get effects, but they won't show up as statistically significant because essentially the two variables are so highly correlated with one another that Stata can't parse out their unique effects, that essentially they're almost representing the same variable. So let's say you had a concern like that. You always just want to take a look at your correlation matrix between your independent variables. So let's just run the correlation between EPI and Gini. I've got a pretty sizable correlation between those two variables. So we might be slightly concerned. But the other thing we can do, slightly more precise test, is to, after you run your regression, type in EStat VIF, and this gives us our variance inflation factors. And essentially these VIFs tell us whether in fact the variable effect is suffering from multicollinearity. And what you're looking for are any VIFs that are high. If they're near 1, that's not a problem. If they're starting to get above 5, upwards towards 10, then you have to be concerned that those variables are suffering from multicollinearity. And usually, if you have multiple variables here, the 2 or 3 that are highly correlated with one another will show up with high VIFs. Okay. So what do you do if you have, if you do have an issue with multicollinearity? A couple of things. One would be to drop one of the offending variables out of a model, run it, and then switch that one back in and take the other one out. And just kind of look at their effects on the dependent variable when the other one isn't present. The other thing you can think about doing is considering creating a composite. But that requires that conceptually those two variables are speaking to the same underlying concept, and maybe they're not. It could just be by chance that they're highly correlated. But if they do speak to the same underlying concept and they're highly correlated and you're suffering from multicollinearity, it may be worth looking into creating a composite. But that's what you do with multicollinearity and how you check for it. Now the other thing you have to worry about is whether you have cases or observations that are really departing from the group and pulling your regression equation, your best fitted regression line, out of whack, and therefore altering the regression coefficients, and essentially biasing your results toward the outlier and away from the majority of cases. And obviously that's something you don't want to have happen. So once you've run your regression, a couple of ways in which we can check for outlier status. I prefer two different ways. One is to check your residuals and your standardized residuals, and that's the distance that your observed cases fall from where you would have predicted them to fall on the dependent variable based on your equation. So the larger your residual, and therefore your standardized residual, the more that case departs from the prediction and is therefore probably altering the overall slope of your line and your coefficients. The other thing is to calculate Cook's D, and that just gives you a measure of how much influence a particular case has on your overall results. So let's just go ahead and start with the standardized residuals. Once you've calculated your regression, what you can do is type in predict y hat. What this is doing is basically telling Stata to calculate a new variable for each case, each state in this case, and calculate using your regression model what we would have predicted social capital to be. Right? There's an observed measure of social capital, but based on our model, what would we have predicted it to be? And you'll notice that a new variable y hat has been created. And after that, we can predict the actual residual. And here, it's just a command where you predict, call it residual, that's going to be the name of the new variable, and then the comma, and then the resid is the actual command telling it to calculate the residual. Okay, again, a new variable called residual. And then we can calculate the standardized version of the residual. Again, we're going to call it R standard and then tell it to use the R standard function. Okay, so 3 new variables created, and we can actually go ahead and look at them. Here's what we would have predicted the social capital index for each state to be, and here's the residual, which is the difference between the predicted and the actual observed social capital value in this case, and then the standardization of that residual. Okay. So now what we want to do is simply list our states, and we can look at their social capital index value. We can look at what we would have predicted them to be, the residual, and the R standard. And we only want to look at them if they meet a certain benchmark, so the absolute value of that. So it's the absolute value of our R standard. We want this to be less than or greater than 1.96, which basically means we got a residualized standard that's much larger than we would have expected more than 5% of the time by chance. And we also want to just exclude any that are missing in this case. Okay. So here it's listing the state, the actual observed level of social capital in that state, what we would have predicted based on our regression equation, 7.74 minus 1.3 times EPI minus 16.5 times Gini. That gives us our actual predicted social capital index value. So we can see that they obviously depart from each other. The residual is simply the difference between those, and the R standard is the standardized residual. Okay. And so what we see, we've got 3 states here that fall above our mark. A couple of them just a little bit, and Nevada a little bit more. So those are the 3 states that we might be concerned at. The other thing we can do is predict a Cook's D. Again, we're going to call it Cook's D and use the Cook's D function to return. We've calculated a new variable called Cook's D. And then we can list state and their Cook's D value if Cook's D is greater than 4 divided by the n. In this case, we had 48 cases in our sample. Okay. And if you want to know what that actual value is, we can just display 4 divided by 48. So that's our benchmark. It's a loose benchmark. And we can see that, in fact, Kentucky's above it, Nevada, South Dakota, and then West Virginia. So both of these are giving us kind of different opinions on outlier status. Here it's showing Nevada, a little bit with North Dakota and West Virginia, but here it's showing West Virginia. Nevada's in the mix as well. A couple of new ones, Kentucky and South Dakota. So based on these, I'm a little concerned about West Virginia and also a little bit about Nevada. So what do you do once you identify your outliers? One of the things I do is create a dummy variable called outlier, make it 0, and then replace it with a 1 if state, in this case, is West Virginia, or state is Nevada. Those are the 2 that kind of pop up in both of these kinds of tests of outlier status. Hit return. So again, here's what your dummy variable now looks like. So now when you run your regression, you have a couple of options. I'll just go ahead and run the original. Now, you could run this if outlier is 0. Right? So now I'm down to 46 cases. I've excluded those West Virginia and Nevada, and I can take a look at my results. And here what you're doing is you're looking at what happens to your R squared. Here we were at 61, and here we're even higher once we got rid of those outliers. And again, because without those outliers pulling my, without being present and creating a lot of error in my predictions, once I exclude them, you'll notice that the overall fit of the model gets better because now my line doesn't have those outliers present. You just have the cases that are closer to it. So I'm doing a better job of explaining variation. The other thing is to keep in mind what happens with your regression coefficients. And so you see a slight change in the size, but the significance levels stay roughly the same. Same thing with Gini, 16.5 to 14.6. Significance levels roughly stay the same. So here's you have an issue. I mean, basically we've excluded our outliers, but our overall pattern result stays the same. In that kind of case, I would probably just leave those outliers in the model and just say that you checked for them and that the overall pattern results did not change much. Now, that said, if your coefficients change dramatically and if the p-values changed, then you probably want to exclude those outliers and stick with the reduced sample. The other thing you can do if you didn't really want to exclude them is, let's run the original model again, and then you could actually just control for them. Control for outlier status, essentially. And what that'll do is it'll allow you to keep the original 48. This outlier status is essentially the effect of being West Virginia or Nevada. Right? And if you're either of those states, it tends to reduce your social capital index even after you've controlled for the other two variables. And you'll notice, again, the coefficients changed a little bit between the original model and this one. Our R-squared went up considerably, again, because we've brought those outliers into the fold. And by bringing them into the fold, by basically controlling for them, they no longer are distorting the effects of EPI and Gini on social capital. So these two variables, these coefficients, are more closely aligning with the majority of cases. So that's one of the other things you can do when you have outliers. Now ideally, what you'll try to figure out is what is it about West Virginia or Nevada that makes them different? Or even South Dakota or some of those other states that kind of popped up on our radar screen. And ideally what you try to do is try to figure out what variables are missing from your model that would essentially do what this variable outlier is doing, which is bringing them back into the fold. So whether it's percent impoverished or something else that we're not accounting for, that would bring those outliers back into the fold. You want to find those things out. So. But that's often not possible to do at any one moment, but is sort of destined for future research. So that's how you check for multicollinearity and outlier status and how you sort of assess the situation and move forward on that.